Hi, I'm Professor Goins, and welcome to the Math Professor's YouTube channel. If you're looking for videos explaining topics in college mathematics, you're in the right spot. Go ahead and click that subscribe button, and let's get into the current video. What I want to take a look at is the geometric series that you will learn about in your Calc 2 course. I want to take a look at the proof of it, or a proof of it. There's numerous proofs, and I'm going to look at one in particular. The theorem says the following. If I have any real number a, and I also have another real number r, where the magnitude of r is less than 1, so r is somewhere between -1 and +1, of course excluding -1 and 1, then if I take the infinite series of the terms a r to the n from 0 to infinity, I have a closed form for that summation, and it's a over 1 minus r. Again, let's prove that. Okay. Well, first of all, let's consider the polynomial f of r. I know we normally use x for our variable, but just so I don't have to convert it to the letter r later, I'm going to use the letter r here. Consider the polynomial f of r is equal to r to the n minus 1, where of course n is going to be a positive integer. So 1, 2, 3, 4, etc. Well, I can see that if I plug 1 into this, of course that's going to be 0. So we can see, or we have r equal to 1 as a 0. Now remember, a 0 of a polynomial corresponds to factors. If I have a 0, I have a factor. If I have a factor, I have a 0. Therefore, I know that f of r has to have a factor of r minus 1. And you know, this is going to hold for any positive integer n. So in case of n is 1, then of course it would just be r minus 1. But if n is 2, 3, 4, then this is a first degree term, and this would be an nth degree term where n is bigger than 1. What that means is there's going to be more terms. I'll just label it as g of r. But I also know that f of r, by definition, was r to the n minus 1. That means r to the n minus 1 is equal to r minus 1 times g of r. Now, I can find g of r by dividing r to the n minus 1 over r minus 1. And this right here is actually applicable for, say, synthetic division. I could use long division, but I think synthetic division allows us to bookkeep a little bit easier. So let's go ahead and use synthetic division. So using synthetic division, I guess it doesn't really show up real well with me standing behind it, and actually that color doesn't look great anyway. Let me pick a different color. Let's see, maybe this one? No, that's still not very good. That's still not great. Let's see. All right, I'll just stick with this color for now. So using synthetic division, remember when I do synthetic division, the number that goes in this box here, half box, is the 0 of the denominator. So in other words, that would be a 1. And then I'm going to go ahead and list the coefficients of what I'm dividing into. So my dividend, the coefficient of r to the n is 1, and then I'm going to have zeros from the power of n minus 1 all the way down to the power of 1, and then I'm going to have minus 1 as my constant. Okay, so I'm going to go ahead and do the synthetic division. 1 drops down, 1 times 1 is 1, 0 plus 1 is 1. 1 times 1 is 1, 0 plus 1 is 1. All the way down to, well then, this would give me 1 times, let's see, that would be this one here, which would be the previous term, would be 1. Add those together, I get 1. 1 times 1 is 1. Add those together and I get 0. So that means that, remember, my last term is my remainder term. Okay? And I know that in the formatting here, the number down here is the coefficient of the polynomial term of 1 degree less. This is the coefficient of r to the n, therefore this is the coefficient of r to the n minus 1, and all the way down. That gives me the following. That says that if I take r to the n minus 1, I divide that by r minus 1. Performing that division gives me r to the n minus 1 plus all the way down to r squared plus r plus 1. Okay? So performing that division gives me this expression right here. Now what I can do is let's write this as a summation. So we would have, let's say, k equals 0 to n minus 1 of r to the k. All right. Now, notice I'm starting to get a series here, and over here I've got a denominator with a difference in it, and that's kind of starting to remind myself of the formula in the conclusion of the geometric series theorem. Well, let's go ahead and take the limit as n goes to infinity. So evaluate the limit as n goes to infinity of the above. Okay, so take the limit as n goes to infinity of both sides. I get the limit of r to the n minus 1 over r minus 1. On the other side, this is equal to the limit as n goes to infinity of the summation okay. Now let me talk about the right hand side while I'm erasing this. Notice that the only place where I have an n on the right hand side is in my upper bound for my summation, and it's n minus 1, but of course if n goes to infinity, then n minus 1 goes to infinity as well, and therefore the right hand side simply becomes the infinite series from k equal to 0 to infinity of r to the k. So I do get my infinite series on the right hand side. Okay. Now let me go ahead and write that, and then we'll talk about the left hand side of that. So this is going to be equal to the sum from k equals 0 to infinity of r to the k. And that should look very similar, other than the missing coefficient of a, which is just a constant multiple. Looks just like this infinite series we have in the geometric series. Now if I look at the right hand side, the only place where I have an n is on as the power on this r. Now remember that the value of r was between minus 1 and 1. And if I start taking powers of that value of r, they're going to get smaller. Just think of a really simple example. Let's say I took a half. Let's say r is a half. And let's take just the first couple of powers. R squared would be a quarter. R cubed would be an eighth. R to the fourth would be 1/16. Those values, as n just goes off to infinity, will converge to 0, and therefore this would give me on the right hand side 0 minus 1 over r minus 1. And I can factor a negative out of the top and the bottom and then cancel that negative, meaning I would get 1 over 1 minus r is equal to the summation r to the k. Now if I multiply both sides by a, I would get a over 1 minus r, and then over here, since this is a convergent series, even if it wasn't a convergent series, I can take constants and multiply them in and out. But the idea is if I put a factor of a here, I could just pop an a on the inside, and I get the exact statement of the geometric series that I stated at the very beginning of the video. Again, this is one proof. There are others, but hopefully this kind of helped give you a little bit of insight into where the geometric formula comes from. Thank you for watching, and please consider subscribing.